Hello and welcome. Here we are in lecture 10. So today we're going to do two things. We're going to do the last 10 minutes of the prior lecture. We didn't get to finish, and then we're going to do the next lecture. So remember in the last lecture, we were talking about testing, right? So we covered our combinational tests, where we kind of built our web programmatically, starting from a Scala functional model. Well, first the component, then the functional model, and kind of build abstractions, right? A way to for a given test case we wanted to run, we could have the model in this interaction with the design automated, and then we could, of course, generate multiple tests and use the model to get a correct answer. So that's what we did. We talked about organisms with Scala tests. And then finally, we finished off with talking about sequential component, in this case, a queue. And we had a really great conversation about, gee, this model I made for sequential queue seems really complicated. Is that a problem? Is that going to reduce our confidence in the verification we're producing by having this testing? Those are some great conversations we had and great questions. And so the answer is, of course, yes, right? So as I was suggesting last time, one thing you want to do when possible when you design your modules and your testing strategy is to control complexity, right? And so one way to control complexity is to have models that are mostly capturing the functional behavior and not necessarily capturing timing behavior. Try and do one at a time. You do only functional or only timing. Only functional, Scala is lazy to do, right? In the case of this queue example, the functionality is pretty simple. And so most of what we were pulling our hair out last time was the timing. And so we're going to do it today. We're going to get into the timing details. If it seems a little complicated, take a deep breath and say, okay, we're just trying to model this queue very carefully, kind of treat it as an example rather than exactly to follow in detail. But it kind of gives a sense of that. Okay, so if you remember for queue, we're using the built-in queue module. Okay, so we built a model, and remember the issue with the model we had was when there's registers in hardware, we want to make sure we read from them before we write to them, because in hardware there is that natural synchronization delay, but in software there isn't. So if we order it correctly, so the reads happen before the writes, we get the right behavior. Otherwise we don't. We talked about, well, what if we were really clever and wrote ourselves maybe a little bit of a helper class that could capture that two-phase behavior of read phase versus the write phase and enforce it automatically. Interesting idea, like a software register in a way. Not a bad idea. But we had our queue model, right? And we ran a scenario where we had a couple of queue interactions. In this case, we are enqueuing one, so we're attempting an enqueue of one. In this case, we're attempting to enqueue two, while we also are saying the dequeue is ready, so it's going to pop something off, right? And so that's what comes off here. At attempt dequeue, we get this option back. And as a reminder, I guess I'll go back to the queue model. We chose to use an option for dequeue to indicate if it's valid or not, right? If it's valid, you get something. If it's not valid, you get none. We could have chosen to, trust the user to know if it's not valid, it doesn't matter, in which case this value wouldn't matter, it's going to be the real value. But this seems like a natural time to try and give more experience using Scala options. Okay, so that was, a simple, very manually written test case. So we're going to try and figure out some abstractions, start kind of building this up to be more manageable, scale up, right? Because otherwise, if we're copying and pasting this every time, it's a lot of work, right? So how about if we want to do a variety of enqueues, right? So what we're going to do here is we're going to have a queue which only has 2 entries. We're going to attempt to enqueue 6 things, so it's going to fill up. Now, the question is, when is this queue accepting a dequeue? Well, we're actually not going to accept a dequeue for the first 3 cycles, right? For 1 through 3, we're going to say it's not dequeue, so definitely make sure that queue fills up. We want to see that back pressure. And then we will see dequeues available, and we'll start draining it. But the entire time, we're trying to enqueue whatever I is, right? So let's go ahead and see what happens when we run this. So we see, for example, in the beginning, we're attempting to enqueue, enqueue valid, enqueue ready, 1, 2. We aren't dequeuing anything. So as a result, after 2, the next cycle, we can see that the the enqueue is no longer ready because it's full, right? So we were ready to enqueue when there's room in this queue, but now the queue is full. We are not ready, right? And so you can see, okay, and then a cycle after that, now this next cycle, all of a sudden, we are now able to dequeue. Now they're able to dequeue because the pipe parameter is true, meaning we can enqueue into a full queue if it's dequeuing. Then all of a sudden the enqueue is now ready and it goes in. So then we try to send 4, 5, and 6. So we try 1 through 6. When we see what comes out the other end, we see, okay, 1 and 2 went through no problem. Then we got 4. And so of course we lost 3 in between because when we were attempting NQ3, it was not ready, right? This is not fire, right? There was valid but no ready. That's not a fire situation. Okay, cool. But yeah, this still seems pretty manual and rough, right? We're kind of just like winging it. So what if we try even more complicated tests? And here we're gonna do something where we're gonna manually write out a test case. I'm just gonna run it and zoom out, but you can see that this, if you're saying, oh my gosh, it seems error prone, you're right. We had this conversation last time. This is why when you make a component, when possible, you want to separate the functionality from the timing behavior, right? If you have a Scala to kind of get the right numerical result and compare that, that's good. The timing is a lot of times a lot harder to kind of model and capture. Okay, and so then I just saw here, we try to imagine a more substantial interaction. And so kind of the model was every cycle kind of copying and pasting what we were doing. And you can see this is kind of very repetitive, right? And in general, whenever you're programming, if you find yourself copying and pasting, it's a sign that there's something you should be automating, right? So that's what this next slide is, hey, what if we go ahead and automate the interaction? So you can see in this case, this harness is quite a bit, right? It's the actual instantiated model, design or test, the DUT, the model, and then the things external to this thing, right? Are we trying to enqueue? Are we ready to dequeue? And if we are trying to enqueue, what data are we trying to enqueue, right? And you can see, okay, given that information, we can pass the rest of this to design, right? So what's nice about this particular harness, we talked about last time about this concern about what if I call, the operations in the wrong order in my queue model because of, the register reading and writing timing. Well, if we put this in one function and I get this right in one place, I can use it everywhere, right? That's kind of the idea. So this simulates one cycle and it gets that interaction hopefully in the right order, right? So we set, the right readies and valids in the right places. You can see, for example, that it's actually taking values from the model, right? So for some of these fields we're not getting for this test case, is seeing how the behaviors should be from the model to know how we're doing, to make sure we're lining up. But the result is we can have these much more concise test cases where we can start saying things like, hey, I want to simulate a cycle and I don't want to enqueue anything or dequeue anything. Okay, I do want to enqueue something and I'm enqueuing 1. Or I don't want to enqueue anything, but I want to dequeue. So that's kind of write this test case much more concisely. And here we are building up abstractions to do that. So cool. There it is. You can see here I have a printf inside my model to kind of print out the content. You can see, oh yeah, it was empty. We enqueued 1 and then we dequeued. Cool. So with that functionality, we can now start putting that inside of loops or whatever. So here we're going to try to fill this thing up and then drain it. And deliberately, we're going to fill it up, to beyond its capacity. And we'll see what happens, right? So you can see, oh yeah, it fills up to 2 and then goes down and comes out. Cool. So piece by piece, we build our web to having its infrastructure, right? And so you can kind of see how it fits together. I think this is the last of this examples. Oh, there's one more. And that is, of course, well, if we have a model, we can make any test case we want now and just check randomly. So here we can randomly enqueue and dequeue. Okay, so you can see here it's trying to enqueue a few times and dequeue. It's random, so we're going to see different behaviors. So we can keep doing this, right? So depending on the module, you might try random, you might try more deliberate things. It varies. But the big picture take from all of this stuff we've been covering, that is, rather than just kind of seeing testing as an obligation, see testing as something that's an opportunity to kind of drive development and get this thing correct. And if it feels like it's really tedious, it's probably a sign you should be automating something, right? So one of the things we're going to do throughout this course, you can see that already for homework 3, getting a Scala model of the functionality first, that way something to compare against. Hopefully the Scala model is correct. You may have to have write tests that are just for Scala to make sure the Scala is correct. And then you can use that in interactions with an automated manner in a test bench to have the model from Scala as well as your Chisel design interact through Chisel tests to actually make sure they match up. For generating tests, we've shown, In this case, manual with some automation or random or brute force, depending on what you're doing. Those are all kind of options out there for you, depending on what you're trying to do. Cool. Any last thoughts on testing or questions, concerns? Okay, cool. Well, then we're going to shift gears to the actual lecture 10. Okay, so normally people talk about functional programming. They have a whole long thing about a lot of formalities. If you haven't already noticed, I'm extremely informal when it comes to this kind of stuff, with a very pragmatic sense. And so what we're going to use functional programming for in this group is a few reasons. Number one, hopefully make us more productive, right? Hopefully we can get our hardware generators more flexible and in fewer lines. If this stuff doesn't work out, we can still fall back to recursion or for plus var, right? So these are still options, but this is still kind of cool to play around with and try it out. And so the big thing to think about when we talk about functional programming in this context is we're talking about recognizing when we're doing things to collections, right? If we're doing something to only one element, technically it's still functional programming, but not in the sense I would be excited about calling it functional programming. Really talking about how we do things to collections, right? So groups of elements at a time. And to go through that, we're going to talk about how this all works. And the reason why we're so collection centric is number one, that's when we're going to use it. But number two, it's also how it works in Chisel. Oh, sorry, in Scala. So in Scala, the functional operations we're going to learn about, things like you see on the slide, map, foreach, zip, those aren't language constructs. Those are functions in the standard library on the collections. The collections implement this function. So that's kind of the point. So it says strength of Scala is the standard collections. This is why you can use really cool functional stuff on them. Let's go play with some code. Okay, we can load up our notebook. Cool. So yeah, as I said, we love building generators in this course, and especially parameterized generators. And so functional programming, so the real goal is number two, we're going to want to do things over collections, right? So over collections, we can have just arbitrary collections of arbitrary sizes or whatever, and we can kind of get the right interactions we want to have happen. Now, as we saw before, right, when we have these collections, we want to do things on them, whether it be a seek or a vec. Sometimes we're doing things like for loops with var, things like recursion. You kind of realize there's some common patterns, right? You kind of keep doing certain iteration or interaction constructs over and over again. And so rather than kind of using these very general constructs to do anything, but repetitively, the idea is, well, why don't we recognize some of these common patterns and make that into a formal operator? And that way, anything that matches that pattern, we can use this formal operator for it, and we can make sure we're conforming to that pattern, right? And so what's nice about this is if you have these patterns and you use these patterns, like I said, other people can read your code really quickly and see what you're doing. Oh yeah, I know that pattern. I've already familiar with that. I don't have to read a loop and try and figure out what you're doing. I know what map means. But also the compiler helps enforce and make sure you're conforming to that pattern, right? And so that's kind of what we're talking about. Now, normally functional programming, one of the kind of key tenets of that in a general sense, not just a collection sense, is an emphasis on immutability, which I've kind of already been sprinkling in this course already. And there's already been places where people have rightly called me out for hiding the mutation behind certain things, whether it be the fact that chisel objects and connect them are internally mutating their connection to information, or when we, for example, when we change our arguments to a recursive call, we're kind of like hiding the mutation in a function call. Same thing's true here. We're going to try our best to do things immutably, but there may be places where we do want side effects, and we need to be very careful to understand how that interacts. Cool. So, like I said, why collections? You want a generator. So generators are kind of a way to kind of put things together. And like I said, we're going to try and find these patterns and put them all together. Cool. So let's go ahead and talk about some of these patterns. How about first two right away, map and for each. So map, as the name implies, for every element in a collection, it's going to take that element, apply a function to it, and then you get an output result. So notice when we keep talking about collections, we're actually being extremely vague, right? We say collections, right? Now in practice in this course, it's almost always going to be a seek, or maybe a vec, or maybe an array buffer. But that's not a requirement, right? Just any kind of aggregate collection of things this is possible for, right? And so map, like I said, it takes every element one to one, right? There's an input, applies a function, takes one argument, which is this input, and it gives you that result. For each is very similar. One element, one application of the function. The difference is that the foreach doesn't have an output you see. So if you want the output, you call map. If you don't want the output, you use foreach. Now, technically, all the places you use foreach, you could use map and just ignore the non-existent output or the unit, void output. However, the point of foreach is to indicate that the point of this is the side effect, right? That like I'm applying this function and there's some side effect here, so hey, programmer beware, this is a side effect intentional thing. That's why we're doing this. Versus map, if you're doing this in the proper sense, there should not be a side effect for these functions. And instead, we care about the output. So it's this input, output, these are different things. This is a mutable copy, this is a mutable copy, and we're applying the function. Cool. Questions so far? Yes. Oh, what do I mean by side effects? By side effects, I mean anything that changes memory, right? So anything that changes the state of anything is a side effect. So yeah, if I have a var somewhere and I change that var, or I have a mutable collection, I change the value inside that mutable collection, that's a side effect. Or in the case of this class, right? If I have a chisel object, even if I just connected to something else, that object's internal state knows I'm connected to something else. That's that now is a side effect. And now it changed something. So yeah. So in chisel, we are going to want side effects sometimes. Things like sorry, 2 slides back. Yeah, we actually do have deliberate side effects. When we connect things, we are changing the state of those objects to say, hey, A is connected to B. That is an intentional side effect. And so as I said, at the end of the day, when it comes to chisel and these generators, never forget that we're instantiating hardware, we're wiring it together. Instantiating hardware, connecting it together. And we're using Scala code wrapped around us to kind of figure out what we're instantiating, how we're connecting it together. Cool. Okay, so then to go about doing this, we're going to need these functions right here. So we're going to talk about a few little details about how these functions are declared in Scala. So maybe a helpful thing will be something called an anonymous function, right? So that is something that, technically Scala would say here is called function literal. Basically, it's a function, but it's so concise and simple. We didn't bother, doing a proper def. It's just an anonymous function. So really, we have syntax already kind of floating around on some of the slides. This operator implies, on the left is arguments, and on the right is the body / return, right? So in this case, we have a single x input coming in, and this function result is x plus 1. So you see that, maybe I'll go ahead and comment this out temporarily. And run that. We made a function. So what this signature here is telling us, this function is something that takes in an int and produces an int. That's what this is telling us. Now, I could assign this function to a val. So I've given a name to this anonymous function. So at this point, it's anonymous, and then I can, in Scala, functions are first-class citizens. They can be they can be pointed to and treated like anything else. So I can go ahead and assign a val to it, no problem. So that val inc, is an int to an int function. That's what it tells you. So given that val, I can go ahead and actually apply it, right? So this is looking up the val, it's finding the anonymous function, and then it's applying it. So I bet you I could even do this without the val. Let's go ahead and try it. This is kind of fun. If I take that anonymous function and then say apply it, yeah. So that's kind of what's going on. Cool. Now, so what the heck is def? We've been using def all quarter. What does def do? So def also binds things. So this index is a little bit different, but same kind of idea. There's a name, an argument list, and then a result. So we defined function inc2. We can go ahead and apply that, no problem. Cool. So naturally the question might be, wait, def, val, what's the difference? So val is going to eagerly evaluate the right side. So usually this is some sort of, operation. Sorry, if it's usually some sort of number, right? If it's like, val a equals 2, yeah, we evaluate 2. 2 is easy to evaluate, and we bind that to a. In this case, the result is a function literal, which is also okay. And so you can have, so you're binding inc to a function, right? But in the case of a def, it's a late evaluation, right? So I could say something like def b equals 2, right? That should also be okay, right? Um, so yeah, but in general for this course, we don't want to overthink this. The simple kind of easy way to get out of this is for references to things, you should use val, and for declaring methods, you should use def. And then for function literals, when we need them, you'll see some more apparent in the next few slides. You can define the literal more directly. So for example, even on its own slide, let's say we want to define a function literal takes in 2 arguments. No problem, right? We can take an a and b and then produce a function takes in 2 ints and produces 1 int. That's what we've defined. Question, yes? You should, you should be able to do both. It should. Well, no, but the evaluation of Inc2 doesn't. So the question for the chat for recording is, okay, can I use a val-defined function and a depth-defined function inside a high-order function? So map is one of the things they call a high-order function. We're going to cover in a second. I believe the answer is yes. I never do this, but the answer should be yes. The reason why I did this is to show that really this is just a literal, and you can save in the reference, right? But normally if you're defining a function, you define it like this. There are some places where actually you define a value rather than a function with a def because you want it to be evaluated later. You want to take advantage of lazy evaluation. Okay, so, yeah. When we use things like map in a second, we'll show you. Yeah, so yeah, let's get right to it. So here we are. We want to do map. And so let's say for this simple case, we want to apply this map function, f to a collection, L, a list, whatever. So we can do whatever this function is to every element one at a time, right? So we just saw inc, right? So we're going to add 1 to things. So you can see that the same syntax many different ways, right? So you can see, for example, we have a range. We can map the def function, no problem. We can do Scala's syntax of not using the punctuation. This is object, operation, argument. And so at first it's kind of surprising, but then you get some very nice English-looking kind of things at times, right? And we saw that in the last lecture with the Chisel test. You say, behavior of this is this, right? And it's like, how is that code? And it's code because it's actually calling a function on an argument, whatever, right? But these two are equivalent. Okay, so in these cases, we're using a named function, right? What if we want to use a function literal, which is more common? Well, so a function literal, usually define it in place. You're trying to do it in line with a map. You do it with the curly braces. So in this case, we're defining a function literal whose body is calling yet another function. That's less common. If you have a function that already exists, you should just call it directly. However, if you don't want to define a function, you can go ahead and just define a literal right here. So all these kind of work. You can see we had 0 through 4 come in. You add 1 to every element, then you get 1 through 5. Or if I change this, fine, I'll make this, times 2, no problem. Why is that one different? Oh, because I only did it on the last line, right? It's only the last line that's changed, that's why. Okay, great. And now let's try the thing we discussed a minute ago. Let's go ahead and try this val-based definition of the function, which I think should still work. It's a little bit weird. Yes, it does. Okay, great. Like I said, it's one of these things in language sometimes I think is an anti-pattern to have things that have overlapping capabilities but subtle differences. I'm more of a risk philosophy, simple and just strip things away. So I would say you get fewer features and it's very clear to use A or B. In this case, if you didn't know any better, you might say, oh, why not use def or val? Which one do you use? Like I said, you read some Scala code, see how things get played out in practice. You use val for references to variables like that, and use def for function. That's kind of the thing. But in terms of the full language ability, you can see that in some cases we can kind of swap for one for the other, and it totally works. But also, this is a much more natural function definition syntax, right? Like this, and this is what they intended you to do. Yeah, go ahead. Yeah. Oh, good question. So I said def is lazily evaluated. After you evaluated it once, uh, what happens? I believe it's evaluated every time. Um, I believe so. Uh, yeah, cool. Actually, you know what? Do we have time? Let's try it real quick. I would say we could goof off for a second and try to make some fake functions, right? So val f equals, let's say it takes in a int, and then let's sneak in some content in here. So actually it didn't evaluate the body here. It left it as a function literal, I guess. And then if I call f, then of course, well, this is a function, but then if I call it on the value, yeah, okay. All right, so it actually didn't actually fully evaluate this. It wasn't as eager as I thought it would be for the val. For def, it's definitely wait till you call it. Yes. Sure. Okay, yeah, good question. So for Jupyter, why is that thing printing in different locations? So what we're seeing is things I deliberately call print line for get put in this little buffer between here and here. Things that are the result of the evaluation of a given line appear down here. So this is the evaluation of all the lines, and then, so you're right, these evaluations are not interspersed with the printouts. So this is the printouts here, this is the evaluations here. So the evaluations, yeah, def inc. L is a range. F is the thing that's defined. And then the result is 4. And then, oh yeah, I called print line inside there. Yeah. Yeah, yeah. So the standard output versus the evaluation of the lines. Yeah, no, great. I'm happy to answer questions. This is perfect. Cool. So, okay, so we have the ability to do map. We showed map, 4 different ways. This is the way you're going to use it mostly, right? Like there's times where when I'm running bigger projects, I will spend the time to run the def function, write the def function as a separate thing because it's like a multi-line function. It's like a 5-line function. Sure, I write a def, give it a name, and then I call map on that name. But for a lot of times in hardware design, you're doing like one tiny little thing. This is all we need. And we're actually going to see what makes it even more concise in like 2 slides. But first we're going to do foreach, right? So foreach is like the exact same thing, except we don't return anything, right? So when we run this evaluation we're seeing here is the original L. There's actually no result from the foreach. It's unit. But as our function, we're calling print lines. So we're calling print line 0, print line 1, print line 2, print line 3. That's what we're getting. So we said, so you could imagine, well, why don't I do this with map, right? And you could. It still calls print line on every single element, but we have this result, right? And this result isn't really needed. It says it's a really key distinction to convey to the reader of your code, users of your code, that I really just want to call this function every element, and there's some side effect. In this case, the side effect being I'm printing to the console that I want to have happen, as opposed to a map where we actually are liberally trying to get the output results. And so if you have side effects in a map, that's poor form. There are some times you want to do both. Sometimes you want to, get the results out and have a return type. You could do a map there, but normally it's going to keep maps pure, right? It just only is producing the output value, or you're having a side effect. If you want to do both, if possible, I would just have 2 code blocks. I have a map block and a for each block on the same collection. Cool. Okay, so let's try it out in Chisel. So let's say, for sake of arguments, maybe I'll comment out this portion, we have something that's going to have a vector of outputs that are all exactly the same value. This is kind of a very silly, obtuse example. Okay, so how might we do that? Well, we're going to have a vec of num elements, right? That's going to be the result of this. So to connect them, we want to connect each output to that constant, right? So here's how we do it. Well, we go through this. Out is going to be a vec, that's a collection. So the Chisel collections also support these same things. So I can call foreach, because in this case, I don't want the return value. I want the side effect. The side effect is, for each one of these outputs, I want to connect it to the constant turned into a uint. So that's pretty cool, right? We could have done something similar to this, like a for loop, right? We could have said, hey, for, I from, 0 until num elements, right? And then we could have said it would have been io.out I colon equals const dot u, right? This should have the same behavior. We can look at the Verilog for a second. Okay, so there we have 2 8s versus here we have the 2 8s, right? So they're two different options side by side. So you might be asking, what are we getting out of this, right? Well, the goal is that, like I said, the point of functional programming in this case is not only help us be more flexible, we can do anything with for loops and bar, right? It's always possible to kind of get done eventually. The question is, can we get this done in a way where we can capture the intent, the pattern here in a way that's get help from the pattern comparing stuff, as well as if you want quickly understand what we're doing, right? So I see a for loop. After reading this line as a reader, all I know is they're going to iterate. I have no idea what's going to come next. Then I read this line. I have to appreciate that, okay, they're taking the iteration space here to iterate across the elements of this collection, and they're doing this operation which has a side effect, right? So it's kind of a few things that they kind of process here. With this functional programming thing, once you're familiar with this, you recognize, oh wait, I'm iterating specifically on the elements here. So now I don't need to worry about interactions between elements. I mean, I'm doing only one element at a time in isolation. That's what this is saying. And if each one of those elements, I'm going to go ahead and connect it to a constant. So eventually, this will hopefully be more concise, not just to write, but also to read what's going on, to understand what's going on, to kind of see it. However, we're learning, it takes time. That being said, it's really easy to write functional programming lines that are extremely concise and are basically unreadable, right? You can definitely take this too far. We're going to see that later on where you start, chaining them together, multiple operations in the same line. They can become unreadable, right? But in the beginning, and why we're using this for this course, and the reason why we're attempted to use this is to try and make it more readable, more easy to get correct, more easy to have the tools help you. Question? Yes. Like I said, so when I discovered that before, right, like I said, map is strictly more general than for each. But the reason why I chose to use for each is because we didn't want the return value, right? In this case, there's a return value of, unit or collection of 2 units, right? And nobody's even saving on the variable, right? So there's a return value no one's even saving, right? As opposed to, and so for each, we're conveying to the reader, hey, I'm doing something where the intent is the side effect. That is the whole point of this. And then we have this kind of toy example here, which actually breaks the code if it's left in there. Here we have, a sequence of, integers, and of course we will map them to uints. We can map them this way, right? That's not too crazy. Cool. So we're going to kind of keep building our way up. It's a little bit of Scala. Tuples. We haven't really covered these so far, but it turns out that you can group together things. So you almost think like tuples is like, you use a Chisel term, an anonymous bundle, right? Or sorry, a bundle with fields are not named, right? It's kind of like you can group together things in a tuple. They can be different types. But the thing about tuple is that there's no names, right? So it's like, I know this is the first element versus the second element. So for example, I have a tuple T1 where I just declare it by, putting 2 things in parentheses and a comma in the middle. I can also go ahead and put a string in there. They don't need to be the same type. And you see here in the type signature, In Scala, tuples are just parens, and then the types are separated by commas. So yeah, this is int versus string int. And now if we're being extra sneaky, I wonder if I can try to implicitly cast this. Nope, I tried to. It says 2 is not a string, right? The correct way to do that would be something like, now it's also a string. Cool. Okay, so that's how you declare them. What can you do with them once they exist? Well, you can access the fields. Now, what's a little bit counterintuitive, and I remember reading Marno Drisky's book, which is the guy who created Scala, the long Scala book, and he tried to justify this, and I forgotten the reasoning, and I don't think I liked it when I read it. They start from 1 on the indexing. So it starts from 1. So this is 2, this is 3, it starts from 1. Also, oddly enough, based on the way the language is designed, there actually is a max tuple size. It's around like 30 or something. So in theory, if you had a really massive tuple, it actually is going to yell at you. But yeah, so you cannot have underscore 1. So it's the tuple dot and then underscore 1 is the first tuple item, underscore 2 the second tuple item, etc. So when it comes to working with these things, they're usually best, because there's no names, to have the production of the tuples and the consumption of tuples to be really near each other, right? Producer and consumer are close to each other. If you have one function in one place of your code making tuples, someplace totally else reading them, it gets confusing, right? Like how to remember what's what. Make a case class. This really easy to make. Make a case class, name the fields. I already know what's what. You can grab it. You don't need to say dot underscore 1, right? If I read this code and I see dot underscore 1, all I know is it's the first element of the tuple. I don't know anything about what its function is, what its purpose is, what you're doing. It's not as readable. That's why a case class is great. So I said, case class gives you names, or if you have things that are homogeneous, right? A collection like a seek is better, right? Because that way you can, easily manage them. In terms of what you can do with it, you also can match it back out. So I have a tuple and I want to get the values separately. Yeah, I can do that too. So I can pull it back out. So you may have seen something similar in Python. You can kind of make tuples and back and forth. Scala has that too. So maybe wondering, why am I talking about tuples? Well, that's for the next operator. So zip, another higher order function. So zip takes 2 collections, and as the name implies, it combines them, right? Element by element. So it takes an element from L1, an element from L2, puts them together into a tuple, and then you have a new collection. So I have a diagram for this. There we go. Yeah, so this is better. So you can see, okay, I have my first collection, the input, and then I call zip on the argument, and then it takes element by element, it goes through, pairs them together, and makes a tuple. So now I have a new collection, which is a collection of tuples, and each tuple is an element from each collection. And so there's a number of times when you kind of find this really helpful, right? So, for example, right, like if I have, in this case, I have something to start off with, I have L1, which is just, some numbers. So I have a collection to play with. Okay, let's say I zip it with itself, right? Well, then I get tuples. I have 0, 0, 1, 1, 2, 2, 3, 3, 4, 4. Okay, cool. Now, everything we talked about so far, we've assumed that both of them are the same length, these collections. Every time I call zip, that's the case. But for full generality, you should be aware that if they are of different sizes, there's no elements for it to zip with, or what's it going to zip with? And so what it does is actually it's going to zip until it runs out of elements, whichever one's shorter. So in this case, we had 0 through 4 on one side and just seek of 8 on the other side. So after one element, it ran out of things to pair it with. Now, the reason why we often want to do this, and this is an example of producing and consuming a tuple in a very close proximity, is right here. We're going to zip these two things together. We know it's going to be this result. And just for sake of having an example, we're now going to apply a map to it. So the map, the element it's working on is a tuple. So each element that's being handed is actually 2 things internally. It sees it as one element, it's a tuple, but it is a tuple, right? And so inside that tuple, we can go ahead and pull out the 2 values, A and B. And then our function in this case is adding them together. Now, maybe wondering what the heck is this word case here? There's a few places where we're doing what they call pattern matching, where you're trying to take a syntax for one thing and kind of have it alias something else. Scala will do it automatically in the cases on its own. Like the prior slide, it did just fine for tuples. That was easy. Some other places, based on the syntax and the grammar, it's ambiguous to the compiler. And so there's cases where we have to use the word keyword case to kind of tell, hey, this is a case, I want you to match a pattern here. And so, yeah, in this case, if you want to pull out the tuples coming in, that's needed. So yeah, in their case, it works together. If I left out this case, we can see the error message it gives us. Right, and you see, yeah, it requires a one argument function, accepting a tuple for two things. And hey, the compiler message again is so good now it even tells me, did you mean to put case there, right? Because remember, if you go back, in this case, why is this syntax ambiguous? Well, without that case statement, it might think I'm trying to give it a function that takes in two arguments, right? Remember, if you go back to the very beginning of the function literals, we said, hey, you could give it, an arbitrary number of parameters before that arrow. So now I'm giving it variables before the arrow, and it can't tell the difference between a multi-input function and a tuple, right? So that's why that case keyword is needed. And with regards to types, in this case, we chose the types in there. We usually can infer stuff pretty well, right? And ta-da, it works again. Cool, yes? Good question. So the question is, wow, it seems like, there's some complexity here about how do we know where case, means certain things, or how do we do certain things? So there's probably a much richer PL theory here about the grammar in terms of what they call pattern matching. This technique is called, and so there's other places where we use case. There's some pretty cool pattern matching. We'll get that in a few lectures where actually you can pattern match on case classes themselves. So in that case, the keyword case makes a heck of a lot of sense. Um, but in general, what pattern matching is so the concern expressed earlier in that comment was, what about strongly typed? It still is strongly typed. It's just an issue of syntax, what's going on, right? The point is, once we, between us and the humans, agree on the grammar and put the grammar into a compiler and a language spec, once we agree on that syntax, there's no ambiguity or runtime variance what's happening here, right? The types are still known, and like it's still making sure these types are compatible. It's just, you're right, the syntax is kind of how it goes. And so in many places for this language, they tried to encourage more concise syntax, much nicer things. It's very productive. But because of the multitude of possibilities in some places, this comes up. As a brief aside, last night I used a class type I've not used in many years that I had read about. I'm like, oh yeah, this is helpful. It solves my problem. It's called an implicit class, right? There's so many different types of classes in Scala. So I use an implicit class, for example. And so I would refer to Scala as a rich language as opposed to a very spare, Go or C-like language is very minimal. Sometimes richness is nice. Sometimes it's like, oh my gosh, this is so confusing. If you read the Scala book, it's this 500-page book. But like in any language, right? Number one, get a minimum viable set of features we can get productive in it. And then if you have the time and the interest, then seek things out to try and learn about the conventions or extra rich features in the language. That blog post I linked to, I showed you earlier in the quarter about this guy Pavel's top 5, Scala mistakes or whatever. And it's like almost everything he showed you or code people would write is correct code. And he shows there was some like built-in feature in the language you would never think to look for to start you there. It does the same thing. And so, yeah, in this case, your comment's well taken about why would we always put a case there? It's not always put a case there, which is why I'm sure some compiler writer was tired of answering this Stack Overflow post and put a really good error message here to tell you, like, I'm pretty sure you meant to put case here. Like, they already telling you the answer right away. Like, they know this is a common concern. And what's interesting now, if you run like a Scala style plugin in IntelliJ, it often tells you to verse. It's like, oh, what you're doing is extra verbose. You actually can remove it. It's like grays things out for you, which is very helpful because I wouldn't know it unless it told me. Cool. Okay, so We did map, we did zip. Oh, sorry, we did map, we did for each, we did zip. Where are we going? Uh, well, we showed the zip diagram. Let's go ahead and do some chisel with this, right? Um, so here's another hypothetical, very abstract example. So we have a vector coming in, a vector coming out. Okay. And what are we going to do with it? Well, we are going to apply the absolute value function to every element, right? So the absolute value function, we're getting pretty good at this, right? We can do this with a mux, for example. We can say, hey, if it's less than 0, invert it. That's a true case. Otherwise, leave it alone. So we just define that as a mux. And hey, here, we can turn this into even what looks like a function, right? This is one of the things we talk about. We're going to have, chisel functions, the return chisel things without being wrapped in the module. Let's go ahead and apply this, right? So before we do the functional programming approach, maybe we could try this with a for loop. This one doesn't even have a bar, right? And it seems to kind of do the right thing, right? You have iteration space using the iteration index to index into these collections. And then, of course, we have our nice handy function, which you already wrote, that does the right thing. So even though I'm going to try and argue the functional programming is nice here, this for loop's also pretty clear. I'm not saying this for loop's bad, right? I'm not saying this is bad. I'm just saying, hey, let's try out functional programming down below. But what do we get when we run this code? Of course, it's going to generate the two muxes, and there's some extra code here where it does the math to do the inversion, right? Where to do it, there's no unary minus in Verilog for this thing, so it has to do 0 minus that thing. So it saves that in a result, and then it puts that in here. And also, of course, Verilog, everything's marked as signed in this case, because they're all essence. Cool, so we can get basically the exact same hardware, but trying out our new handy-dandy higher order functional functions here, right? So we can take in the outputs, zip them with the inputs. And so then when I made this tuple and I pattern matched on it, I chose to make it really clear to myself, O for output, I for input, and I can connect them, right? Okay, the output's connected to the absolute value of the input. And we get the same hardware. So this is pretty cool, right? It's just like, man, we just like drop some stuff and all of a sudden, it is kind of cool combination of stuff. In terms of how this plays out in practice, for stuff we're going to see in a few slides, I'm going to show some examples. You get a lot of the bang with map, for each, and zip in a few places, right? Zip when you're trying to combine two bundles or two vecs or whatever. There are additional higher order functions we're going to cover on Friday and even next week. Those ones get used less and less, but they're kind of good to be aware of. I actually more often use those in the Scala functional models rather than the Chisel. But yeah, questions so far? Cool. Okay. Let's keep going. So I put this thing much later in the lecture than we might have thought otherwise. You've seen the syntax probably already in the course accidentally, but now let's talk about it. So Scala is something called function placeholders, or I call them wildcards, even though they aren't wildcards. So if you hear me say that, just know I'm saying it wrong. You can see the benefit right here. If I have a single argument function, rather than saying I want a single argument and then to apply it, I can just contract it out to just being take the argument and then apply it this way. So in some cases, the syntax is extremely concise and really nice. The reason why I have this slide later is that this thing, if you're not careful, can confuse you and you get the wrong result. One thing that comes out, and let's say your goal is to square something, right? I times I. You actually can't do that with this literal thing, right? If I try this, it's going to yell at me. And the reason why is every time you use the underscore, it uses up one of those arguments, right? So if I have multiple underscores, that means I have to have multiple arguments. And so I want to reuse the same argument multiple times. Then you need to just name your arguments and do it normally. This only works when you're going to use each argument exactly once, and they are applied left to right. So if you know I have two arguments, okay, left to right, fine, that's fine. But if you have like 4 arguments, I would not use these kinds of Scala placeholders. It'd be very confusing. But when there's only one thing, yeah, that's really clear, right? Take all the elements and just add 1 to each element, right? So rather than defining x and then saying x plus 1, let's just go ahead and put a function placeholder in there. Cool. Okay, so now that we have all this cool handy stuff put together, we're going to go back to our arbiter from last week. So remember we did the arbiter in multiple passes, and this was our second draft, right? Our second draft, we had multiple for loops. It got down to fewer for loops, and we already were kind of reusing components, right? We're already reusing Chisel's priority encoder. We're already using, mux one hot. Remember the whole point of our arbiter was we had in all of these decoupled inputs coming in, and they're all making a request, and we have a decoupled output. And if the decoupled output is ready, that means we're able to, service one of these inputs, right? And then in this case, we have a fixed priority, right? But you can imagine we had more sophisticated priorities otherwise. And so this is from last time or 2 times ago, right? And this is the code we came up with, right? So we had all this work here, right? We're kind of trying to pull out all these valids, so we made a wire of vec in advance, same thing for all the bits. And then we went ahead and, in the for loop went through, okay, we went out and grabbed all the valids, all the bits. There's also the return path for each of these inputs on the ready signal. And well, that's going to be based on, is it chosen and are we firing, right? Well, here we are making use of abstractions, right? This isn't like, poor code, right? We, fed in all of our valid signals into the priority encoder to find who wins. And then because that's a one hot output, we can just peel off those bits bit by bit to kind of pass them out to the things. Taking advantage of the fact this is decoupled, we can just call .fire when it fires. So there's some nice parts to this code, but there's still kind of a lot going on. We're declaring wires, we're connecting wires over here, and then we're indexing things. There's a lot going on. Okay, so now with functional programming, it's a little simpler, right? So what do we do? Let's start with the thing for valids. So for valids, we had declared a wire of vec. We had to go in and grab them in one place, and then, and even notice here we actually worked on it out of order, right? Here we are using that as an input to something else before we even assigned it, right? This is the difference between, hardware versus software. It's all spatial. So we're defining valids, we're using valids, and we actually define what valids connected to, right? And that works totally fine because in this case, this is taking the output of valids. Meanwhile, this is setting the inputs to valids. So it's totally fine to do them in 2 different phases. Okay, so here we had three things, right? There's declaring valids, connecting up valids, and then using valids. Okay, what about over here? Well, we can just grab all those fields with a map, right? So the point of this is what's returned. So map makes the most sense. Okay, we go in and grab all the valids. So in this case, we're saying io.rec. So each of these, elements. Yeah, we're just saying, hey, give me the valid on them. Cool. If you go back to the prior slide, we were setting our output valid based on the invalids or reduction. That is unchanged. The interesting difference is, notice how in the prior one, because invalids already was a wire of vec, we only had to cast that to a unit in order to do OR reduction. While over here, at this point, invalids is actually a sequence of bools, right? And so we actually first need to put those into a vec and then call as you went. Don't worry, this combination of hardware, as scary as it looks, is not going to produce a bunch of extra wrapping Verilog. It's just a matter of type playing around in Chisel. But this is the other stuff, right? For example, chosen one hot, priority encoder from invalids, that's unchanged. Okay. So then there's this entire for loop. We eliminated one line with invalids. What are the other 2 lines? How do we get rid of those? Let's go ahead and see those, right? So, for example, you may notice that there's no bits variable here, right? So wait, what happened to bits? Well, what happened to bits is over here we went through the effort of making a wire vec of whole bits. We connect them all up with the for loop. And then when it comes time to produce the output, we use this one hot mux, which can use that chosen one hot, so also working on one hot. And then we get bits. As a small aside, this naming thing's been there since the beginning, and I don't like it, where for the mux, it's one hot. For priority encoder, it's one hot. And it's like, oh my gosh, pick one. Sorry, small detail. They're both one hot. Anyways, yeah, so what happened to bits? Well, we are doing a mux one hot using chosen one hot. We just didn't bother to declare a bits variable because we can just grab the bits, right? So you're going effort to make a bits variable and connect it and do it all over. This has the same connectivity, right? We can just map all the bits fields. So why bother making a variable for that? We can just plop it in right there. And so you kind of start seeing some of that functional programming productivity. We can kind of quickly operate in collections. Notice how there's no loops here, and they're working on a lot of things, right? And the reason why is working on things in terms of collections, right? Okay, give me all these IOs. This is a big vec, great. And for each one of these things, give me the bits fields, right? Now just collection of bits. Okay, I'm going to feed those collection of bits into a mux, which takes collections, and then that mux is going to be the one in the hardware selects what we're taking. And then the finale. Okay, so we had to generate these ready signals going backwards. What's going to happen with that? Well, let's see. So we're going to take the IO request, and we're going to zip that with the chosen one hot. So in other words, IO port 1 is going to be associated with chosen one hot bit 1. Okay, so I have my IO and my chosen bit. So that IO is a decoupled thing, so I can take its ready field. I can connect it to chosen and IO.fire, and this is that chosen bit for it. So it's actually exactly this line we just saw, right? So this line where we were using the for loop indices to grab things. Alternatively, we can do a zip and a foreach. So that's the kind of the alternative. And so, yeah, this should compile. So you can see this is more compact. Is this guaranteed to be more clear or less error prone than the other one? I wouldn't go that far. But here we are kind of playing this stuff out and see what we can do with it. And maybe, as we said, I would give it a chance in this class, see what you think about these functional programming constructs, these high order functions, and play with them. And for some of our assignments, we're going to kind of mandate you use them in certain places. And then you'll kind of see what makes sense. And you kind of can play with it and start thinking at a higher level how to kind of put things together. And so, yeah, you can have some really cool code where, there's no loops. You're just working in collections and kind of move things between collections. Sometimes it's more readable. Like, to me, this is really clear what you want. Okay, I just want all the invalids. To me, this is a pretty clear win. Other places like this one, maybe that's more clear. Maybe that's not more clear. I don't know. I think there's some subjectivity in that one. And as I said, so worst comes to worst, you can fall back to 4. There's nothing wrong with 4. It works. But we'll see some additional constructs when we cover more higher order functions that it's not so easy for 4 to do. So in this case, everything we've been doing for the most part has been element-wise, right? Map, foreach, zip is kind of like, okay, element by element. Some of the other ones we'll be covering are more aggregation, reducing kind of things that actually have a bit more of that kind of stuff to them. Cool. Questions? Okay. All right. Well, that's all. Have a good day, folks.